Hello, if you're watching this, hopefully that means you've walked through the conversions, the binary, hexadecimal, decimal conversions with us. And now this short lecture, hopefully I'll keep it at 5 to 10 minutes, just tells you why it's important, why it's so important to know how to do binary and hexadecimal conversions and how to do all of that. It all has to do with how different types of data are actually stored into a computer as memory. And so it all has to do with storing information. You guys know that computers don't just store whole numbers, and they don't just store binary numbers. They'd actually be quite useless if that's all they did. They would have very limited capabilities, and very small groups of people would use them. You think back to sort of the first generation of computers, only the government could use those, and a few really big corporations. And so now computers actually store quite a bit of types of information. Before I show you the 6 main types, I want you to guess. What else is stored in the memory of your computer? Think about it. Well, here are the 6 big things stored in your computer. 1, we store whole numbers. 2, we store negative numbers. How do we store a negative number in a computer? You can't have a negative transistor. If you reverse the flow of the current through the transistor, the computer has no way of knowing that the current's going one way or another. You could design it to know, but that would take a lot of work on a hardware side to make hardware really expensive. You also have fractional numbers in a computer. You can't flip a transistor halfway on, and you certainly can't flip a transistor 0.24369 on, and you can't flip it to even pi. You can't have 3.14159. Right? And so how do we store fractional numbers is on and off light switches. We're going to talk about that. Then you have the big other 3, the major 3. I was playing a video game today, and it was stored as these 3 things. Very few numbers, but it was all text, images, and sound waves, which, by the way, is what movies are too. The movies you watch on Netflix are not numbers. It's if they were numbers on a screen, it'd be very boring. And so you have to save text, images, and sound waves, but all of these have to be brought back to ones and zeros. That they have to be. So over the years, we've developed some really clever ways of saving these numbers in a computer in such a way a monitor can understand them and display what's on your screen. So let's talk about the easy one first, which is whole numbers. Actually, we're not going to talk about that first. Let's talk first about the first step of saving information is you have to divide your binary bits up. And so we have divided the binary bits up into sections, which helps us store information in really important ways. And so you guys know that one transistor is a binary bit. It's saved as a 0 or a 1. And so then 4 bits we call a nibble. And so an example of that is 1111, and then 2 nibbles is a byte. So any binary number you have, we went over this with conversions, you divide up in the 4 sections of 4 for the nibbles, and then the 8s are the byte. And then a word is anything beyond that. We say it's a binary word, and usually binary words are 16, 32, or 64 bits. At that point, you're just adding digits onto the end to the bytes, and so that's called a word. A word is different in every different way, and so the first thing to understand before you store anything is you're storing it as nibbles or bytes. You're storing, or even words, and so sections of code. Usually, when memory is being transferred over to the processor through the bus lines, it's being regulated through those at a time. So it will send 4 beeps at a time, or will store 64 bits at a time, depending on how the hardware is set up. So once you've done that, once you've divided it up like that, you can understand how we can save information. So the first type is a whole number. Easy peasy, it's just saved as its binary hexadecimal counterpart. So, 1000 is 8. So if I want to store an 8 in my computer, I just flip 1 transistor on in the nibble and leave the other 3 off. If I want to store the number 16, then I increase it to a byte, and it's 0001, 0000, right? That's 16. And so whole numbers are just saved as binary. That's the easiest thing to do. That's really what we've been working on all week. So that's not hard. But what happens when the number is negative? What happens if I have a negative number? Well, they invented a way called 2's complementing, where every number, whether it's positive or it's negative, is made the same length using what's called leading zeros. And so you guys know that if I wanted to write the number 2, I could just write a 2, or I could write the number 2 as 00002. 0.000, right? If I wanted to write 138, I could say 00138 0.00, right? Usually we use leading zeros when we're doing money. Money is when we use that. And so it's the same with negative numbers. Every number in a computer is actually saved as the same word. Remember, a word is a certain length of numbers, right? And the word size you use, whether it's a byte or whether it's 16, 32, 64, 128, is going to dictate how many numbers you can save in your computer, right? If I only am using a nibble, then I can only count up to 7. Which isn't good. And so, but that's the start, right? We make every number the same length, and we make it the same word size using leading zeros. So here, I've taken 1010 and made it a byte, right? With the first 4 switches off, and then the fourth and second one on, and the first and third one off, right? And so then, if it's positive, I just leave it alone. If it's positive, I just leave it. But if the number is negative, then you flip the value of each bit. And so now, if it's negative 110, which would be negative 10 in decimal, because it's 8 plus 2, now I would save negative 10 as 11110101, which helps the computer know. But then I add another 1 to the entire number, just to give the computer an indication. And so then we've move the very last one on the right there to the second digit, and that's called 2's complementing. The good news is I'm not going to make you do any 2's complementing in class. We've already broken our brains doing the other conversions this week, yet it is important you know that negative numbers are saved using 2's complementing, and you use leading zeros, save everything the same bit, and add a 1 to the entire number. And in more advanced computer classes, you'll revisit this, but right now you just need to know that's how it's done. Very clever way of doing it. Then, if I have a fractional number, here's how it's saved. You've already seen this on a calculator. You've seen the number 1345E1 on a calculator, or a number like that. You've seen that number E, that letter E, right? And that is, we save the numbers as the scientific notation, or what's called a floating point. And so that just saves 2 additional things about the number. When any number is saved, it saves 2 additional things about them. It saves how many digits the number is. That's called a mantissa. So this is how many digits we have. And then it saves at what digit do we put the decimal, and it uses an E there and a number. And so 1.345 in your computer is actually saved as 1345E1, meaning the decimal goes right after the first digit. If it was E0, it'd be 0.1345. If it was E2, it'd be 13.45. If it was E3, it'd be 134.5, and so on and so forth. You get the idea. It just tells you after what digit to put it. So it uses a mantissa and an exponent using scientific notation. So that's fractional numbers. Text, then, is a little bit more complicated. Text uses what's called a coding scheme. And there are actually 3 of them. But basically, this idea is that every single character and symbol is assigned its own binary number. And the monitor is hardwired such to read the binary number and know what letter to put on the screen. Your keyboards are wired that way, too. So every letter and every symbol has a number. So ASCII, which stands for, I have it right here. It stands for the American Standard Code for Information Exchange, which you don't need to know, information interchange. It was the early one of the first ones, and it used 7-bit numbers, which means you could count 120 characters. So they named 128 characters. The English alphabet was in there. The uppercase and lowercase get you 48 of them, and then the number symbol, the $sign, the hashtag, parentheses, question marks, periods, all that stuff you see on your keyboard. If you look down at your keyboard right now, that's all saved. Every single one of those has a binary number equivalent up to 128 of them. The problem was we ran out. There's more than 128 characters at work in the world, especially when you add sort of the Asian languages, which use different alphabets altogether and different symbols. So at one point they extended it. It's called extended ASCII, and they extended just 1 bit, which actually doubled the amount of characters they could save, so to 256, but then they ran out of those, so now most everything's Unicode, which is 16 bits, and it allows for 34,000 characters, which I don't think we're ever going to touch, but emojis are actually being now saved in that, so emojis are being added to the 34,168, so if you guys look, you can, every once in a while an article comes forward that says they've added a new emoji, and they've assigned it its own binary number, so it has the same status as the letter of the alphabet, or the number symbol, or the percentage sign, or the period. So that's kind of cool. Unicode is every single letter takes up 16 bits on your 16-bit word on your hard drive, and that allows us for 34,000 symbols. And so we'll get there eventually, I'm sure. So that's text. And then images we've talked about in this class. It uses RGB encoding. So every pixel begins white, and the computer is told, there's a command that says subtract this much red, green, and blue out of it. That gives you all the colors of the world. So that means each pixel is saved using a 6-digit decimal number, which is a 24-bit decimal binary number. That's a typo right there. It's a 24-bit binary number. So the first 8 bits tell the monitor how much red to take out of the white. The next 8 to say how much green, and the next 8 how much blue. So images use RGB encoding. Every pixel has a 24-bit binary number, and the first 8 say subtract this percentage of red out, subtract this percentage of green and blue. And so if you have a pixel saved as 009900, that would be straight green. If it was 990000, that'd be straight red. So if it's 000000, that'd be black, right? 999999 would be white. So that's how images work. And last but not least, we have sounds. Sounds are, I think, some of the more fascinating ones, and that's just every once in a while, depending on the sample size. So when you save a sound wave to your computer, you actually dictate the sample size. Usually you do it by saying, I want this HD, or I want this SD, or I want this UHD for ultra high definition. And depending on that size, the computer will check in on the sound every once in a while, and it will save the amplitude, which is how high the wave was, and the time or the beat of the wave, meaning how often it repeats, and it will save that as a 4-digit number. Songs with a high sample size are sampled all the time. It may be sampled 10 times a second, and those are your HD songs. Or SD songs might just be sampled 1 time a second. But the sample size is going to dictate how well you can hear the song. HD songs sound better. SD songs don't sound that good because the computer's actually jumping from sample to sample, and so if you only sample it every second, you're missing what's between that second. So if the song changes a lot, you get a low quality song and a lot of buzzing and stuff like that. So sampling checks in and says, okay, how big's the wave, and how often does it repeat, and it's saved that way. So, and you can save all the song waves of the universe that way, which is kind of crazy. So that's how we store information, as binary bits or their hexadecimal counterparts. So these will be the quiz questions, so make sure you have this open maybe while you're clicking through the quiz this week, and hopefully you learned something. I think all this is fascinating, by the way. So have a good one.